let's now talk about some things that led to modern atomic theory. Modern is a bit of a relative term because we're going to start back in 1789. So there's this French guy, his name's Antoine Lavoisier, and he came up with the law of conservation of mass, which you have probably heard of before. He says, in a chemical reaction, matter is neither created nor destroyed. So we've heard about that for a while. Then, a few years later, guess what? He got a Nobel Prize. Another guy, Joseph Proust, makes another Nobel Prize. He's also French. And he comes up with something, we call it the law of definite proportions. The law of definite proportions says that all samples of a given compound, regardless of their source or how they were prepared, they have the same proportions, if you prefer ratio, that's fine, of their constituent elements. So let's kind of talk about what this means. So in conservation of mass, I wanted to tell you both of these, and then I'm gonna give a few examples. So conservation of mass, energy is not created nor destroyed. So if we have 7.7 grams of sodium, we have 11.9 grams of chlorine, we're going to end up making 19.6 grams of sodium chloride. So here, take your little calculator out. What is 7.7 plus 11.9? Look, 19.6 equals 19.6. So same amounts. Now, proportions. There's another video that I have posted on Blackboard. It's not one of my videos, but it has to do with water electrolysis. So if you watch that, or I show it in class, what happens is if you run a current through a sample of water, you're going to get, so here, these are inverted test tubes. Here's your water. You've got a battery. And so here you have a positive and a negative, and you're running your current through it. This looks terrible. But it's going to break water up into hydrogen and oxygen. Well, you should probably know the formula for water is H2O. Well, the amount of gas you get, you have twice as much hydrogen as you do oxygen. So there's 2 to 1. So the proportion in water is always twice as much hydrogen as there is oxygen. So definite proportions. If it's water, this is how it exists. So the water electrolysis video is pretty cool. So if you run the current, you're going to get twice the volume of hydrogen gas versus oxygen gas. We'll actually talk about electrolysis in 180 in chapter 19, if you stick with me that long. I hope you do. So let's do a demonstration here. 2 samples, carbon monoxide. We're going to break them down into their elements. One produces 17.2 grams of oxygen, 12.9 grams of carbon. The other one, 10.5 grams of oxygen, 7.88 grams of carbon. And let's show that these are consistent. So one of the things we do in chemistry is we work a lot of word problems. So the first thing, we got to make some sense out of this. So let's kind of sort out what we've got. So one sample, I'm going to call that sample 1. Mass of oxygen, 17.2 grams. Mass of carbon, 12.9 grams. And 10.5 grams, 7.88 grams. Okay, so now that we've figured out which goes with which. And I mean, sometimes I like draw arrows on here. You know, you'll see me underline and circle stuff in the problem that just draws attention to itself. So that helps me keep from getting confused. So now let's find the mass ratio, because we're talking about a proportion for oxygen and carbon. So in sample 1, we have 17.2 grams of oxygen, 12.9 grams of carbon. Let's put that in the calculator. Let's see what we get. 17.2 divided by 12.9. 1.33. We get 1, 2, 3 significant figures. See, it's good practice. Let's do it again in the second one. 10.5 grams of oxygen, 7.88 grams of carbon. Now, if you were somebody and you put carbon on top and oxygen on bottom, that's fine. Make sure you do it the same way so you can make a valid comparison. Otherwise, you won't be able to compare them properly. 10.5 divided by 7.88. Look, 1.33. Is it exact? Not quite, but pretty much, you know what, I'm going to say this is the same. So this is consistent with the law of definite proportions. Now, let's try this. We have 2 samples. We're going to decompose them. One sample produces 38.9 grams of carbon and 448 grams of chlorine. The other sample is 14.8 grams of carbon and 134 grams of chlorine. Now, are these consistent with the law of definite proportions? Let's find out. This says chlorine on top, carbon on the bottom. So 448 divided by 38.9 grams. So let's see what we get. 448 divided by 38.9. 11.5. Okay, now let's do this one. 134 over 14.8. What'd you get? 9.05. Is that consistent with the law of definite proportions? No, it is not. They should be the same. So, these are the results of an experiment. So, you know that they should be the same, but they're not. So, I'm going to teach you something. So, when you're in lab and you get results that go, that can't be right. That's not what's supposed to happen. So, you should perform an error analysis and say, well, that's not the answer I was expecting. What could have gone wrong or whatever. Okay, so let's say, so you go through, well, did I do my math right? Okay, well, yeah, I set it up right. So, yeah, I did the math right. Okay, so there had to be a flaw in the experiment. Well, what could have happened? Well, okay, so chlorine's a gas. Well, what happens if maybe you had a hole in the gas tube? Maybe some gas escaped. Maybe some leaked. And so you say, okay, let me try it again. So you try it again. And so you have your sample. And so this time you get 14.8. But this time you also get 170. So what happens when you get 170 grams, 14.8. Oh, look, 11.5. This is the correct one. You say, uh-oh, something went wrong in there. And you don't get mad at yourself. You have to start thinking in your head, what could have gone wrong? That's not the answer I expected. And, you know, that's something we try to teach in the laboratory, is it's about how to think. It's not always about, oh, but I didn't get the right answer. People that win awards got many wrong answers. And so then it's about teaching you to think, well, what could I have done better? What could the experiment have done better? What could have happened? Things like that. Now, let's talk about the law of multiple proportions. So, definite proportions, multiple proportions. This is different. It says, when two elements, we're going to call them element A and element B, when they form two different compounds, the masses of element B that combine with the same amount, in this case 1 gram of element A, we can express them as a ratio of small whole numbers. And so that was from a guy named John Dalton. We'll talk about him several times. Very brilliant. Won several Nobel Prizes. So when we have carbon combining with oxygen, it forms two different compounds. So let's kind of take a look here. So carbon is going to be element A, oxygen is going to be element B. So in carbon dioxide, 1 gram combines with 2.67 grams. In compound 2, carbon monoxide, 1 gram combines with 1.33 grams of oxygen. So let's kind of see what happens. So here we have the same amount of carbon. So when we're doing our multiple proportions, we're going to check out this oxygen ratio. So let's call it the oxygen ratio. So here, 2.67 divided by 1.33. What is that ratio? 2.67 divided by 1.33. 2. So this compound has twice as much oxygen as this one. All right. So now let's look at another one. Hydrogen oxygen can form water or can form hydrogen peroxide. When we decompose water, we get, make sure I get this table right, 0.125 grams of hydrogen. 0.125 grams of hydrogen for every 1.00 grams of oxygen. I'll put grams on there. And in hydrogen peroxide, we get 0.250 grams of hydrogen for every 1 gram of oxygen. So here, this is staying the same. Let's look at what changed. So for our hydrogen, this should be a ratio of small whole numbers. So 0.125, 0.250. So our ratio is 1 to 2. So look, this has 1 oxygen, this has 2 oxygens. How about that? So 1 to 2, if you prefer that notation. Now let's look. Nitrogen makes 5 different compounds with oxygen. So here you have the same amount of nitrogen, 14 grams. For the first compound you have 8 grams, 16, 24, 32, and 40. All of these are multiples of what kind of number? What is their greatest common factor? I hope you said 8. So here this would be 2, 1, 3 to 1, 4 to 1, 5 to 1. So it just kind of goes there. So again, multiple proportions, one thing is held constant, something else changes. You should get a ratio of small whole numbers. So John Dalton used conservation of mass. He used definite proportions and multiple proportions to formulate his atomic theory. Dalton's atomic theory, which was the first atomic theory that anyone came up with that made any sense, said each atom is composed of tiny indestructible particles, and we're going to call them atoms. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. And then atoms combine in simple whole number ratios to form compounds. And atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way they are bound together with other atoms. So this is like, we're not creating or destroying anything there. Now, he comes up with this in the early 1800s. Based on the things that we're going to learn in the rest of this chapter, he really wasn't that far off based on what we know today. So we'll get into that shortly.